In this paper, we present a method for optimizing the design of fluidic devices for desired user functions. Our contributions include a fast, smooth, physically based steady-state Stokes flow simulation with explicit handling of a variety of boundary conditions, a scheme for differentiating the simulation with respect to a parameterized level set morphology, enabling fast gradient-based optimization of fluidic devices, demonstrations in the automated development of 2D and 3D fluidic structures. Our solution is comprised of three components: parametric level set boundaries separating solid matter from fluid flow, fast differentiable steady-state simulation, and efficient gradient-based optimization. Our level set boundaries provide an expressive means of parameterizing the design space of fluidic devices with few parameters, making design optimization tractable. During the initial design process, users specify an initial boundary design from our set of spline-based primitives, as well as flow boundary conditions, such as inflow location and velocity, and desired output flow. During optimization, the parameters of the specified design primitives are iteratively optimized to generate new geometry with improved function. Our optimization framework relies on fast simulation in order to evaluate ever-improving designs. Our framework formulates steady-state Stokes flow as the solution of a quadratic problem. This means simulation can be performed quickly by employing fast, linear solvers. Gradients can also be computed quickly, allowing for efficient gradient-based optimization of designs in a matter of minutes. In this flow averager device, the total velocity from the inlets on the left must be averaged to create two channels of equal flow velocity on the outlets on the right. Our algorithm is able to optimize the boundary to find a device that averages the flows. Here, we show that the optimized design works over a wide range of sample inlet velocities. In the funnel problem, perpendicular flows from an input in the x direction and an input in the y direction must be combined to an outlet flow with an equal x and y component. Here, we show the optimization performed by ensuring the device works in two extreme scenarios: one where the x input flow is 0 and one where the y input flow is 0. The superposition gate composes two input flows, one along the x-axis and one along the y-axis, to create an output flow that is the sum of each of these components. The optimized flow is valid over any input combination and varies smoothly. This fluidic twister device must translate inlet linear flow at the top to a spiraling flow on the bottom. Here, we highlight the difference between optimized results using the no-slip and no-separation boundary conditions. The lack of friction is critical in enabling this behavior. The cross-section of the flow along the optimized shape surface properly achieves a helical motion. This is a fluidic switch. The inlet flow on the left must be fully routed to the top or bottom channels, depending on the orientation of the center geometry. That center geometry can rotate along the vertical axis. Its NURB surface is parameterized by a collection of 32 control point positions, which can have a significant effect on the outlet flows. Here we show the evolution of the design during optimization, along with the resultant outlet flows in both configurations. The optimized flow is smooth and smoothly translates flow from one outlet to another as the switch is turned.